then I do some algebra, and it turns out that this x equals 0.0585, which is 5.85% if I multiply that by 100. So this is my percent abundance of my V50. 1 minus x is 0.9415. Multiply by 100, we get 94.1%. This is my percent abundance of vanadium-51. Now, that trick only works if you have two elements. If you have more than two elements, right, you're not going to be able to do that. Now, what they may do to you in a problem is they could say, they could give you three different isotopes and give you one of the percent abundances. And then you could actually do a similar thing, all right, with your x's. All right? And I think there's one like that in the homework. All right. So, how do we come up in nature? How do we come up with these percent abundances? And we use a machine called a mass spectrometer. So, the mass spectroscopy or a mass spectrometer is used to study the composition of different substances. I wish we had a mass spectrometer, but we don't. Okay, they're tons and tons and tons of money. All right. For those of you that take forensics, all right, you'll talk a lot about mass spectroscopy. All right. So in real life, crime labs have a mass spectrometer. All right, and they're used to identify different substances that are in evidence. Okay, it identifies drugs. All right, it'll identify poisons, that kind of stuff. Let's see, things that we do with a mass spectrometer. We use it for radioactive dating. Drug testing. Let's just say compound analysis. Okay, so if I want to know what compound's in a sample, and we use it to find our relative abundances of isotopes. Okay, so this mass spectrometer is pretty useful tool. Now, how does a mass spectrometer work? So in the machine, the very first thing we do is we ionize the sample. Once it's ionized, once the atoms actually have a charge, okay, the ions that are formed from the sample are passed through an electric field. Those particles react to the electric field because they have a charge. So once we put them in that electric field, they accelerate at different speeds due to the difference in mass. So if you remember back to physics, it takes more energy to move a heavier object. So when we speed these up, let's just say lighter ions move faster, heavier ions move slower. And this difference in speed actually separates out the different ions by mass. All right, and we get, actually it spits out a graph. All right, so there's a nice picture of this in the textbook. All right, so make sure you look at it, okay? So there's a nice picture in the textbook of that mass spectrometer and how it works. So now, once we do this acceleration, it measures the different masses of the sample that's in there, okay? So, and that's what gives us our percent abundance, and it gives us a graph. Okay, so once we've done, okay, so we ionize the sample, we pass it through the electric fields, okay, we have the different ions moving at different speeds, and then there's a detector. So the detector measures the number of particles of each mass. And it gives us, the machine gives us, a mass spectrum. And it's a graph, or a plot, of percent abundance versus relative mass. So this is the process that occurs in the machine. Right? And I want to show you a example of the graph that it would spit out. Okay, you need to be able to work with these. All right, so let's say that we're analyzing a sample of neon. So when we analyze neon, okay, neon turns out has 3 isotopes, okay, and it gives us relative abundances. So when it analyzes it, we would get something like that. 20 would go all the way up to 100, 21 is pretty small, and then 22 is something like that. So we get this graph, and it gives us the numbers. Percent abundance, okay, for 20 is 100, 21 is 0.3, and 22 is 10.2. Right, so it gives us this percent abundance. Now, what is this really telling me? Well, first of all, it tells us that there are 3 isotopes. Okay, so we know that 2021, okay, so this graph tells us that that sample of neon, it has 3 isotopes. Second thing it tells me, neon 20 is the most common. Neon 20 by far, so the larger this, okay, the bigger the value up here, okay, obviously it's much more abundant than 20 and 22, or excuse me, 21 and 22. This height is actually not the number of ions that are counted. The height indicates the proportion of the various masses. It's the proportion of the various masses. We can use this, okay, we can use this data to actually calculate the average mass of neon. And you need to be able to do it, and it's simple. Okay, so it's a little bit different than our weighted average, but it's pretty similar. So it's just 3 steps. When we're going to calculate the average mass using spectrometer data, the first thing you're going to do is you're going to add your percent abundances together. So we take 100. Crap, sorry, this is 100.0. We need it for sig figs. So we have 100.0, 0.3, and 10.2. We're going to add all that, and we get 10.5. This is actually our total number of ions. That's our total number of ions. The next thing we need to do is we need to get total mass. And we use our weighted average kind of thing. So we know that we have 100.0 ions of neon 20. We have 0.3 ions of 21. And we have 10.2 ions of 22. When we put that all together, we get 2,230.7 AMUs. This is the total mass of all the ions. This is the number of ions. This is the total mass of the ions. Now I can actually calculate the average mass. and I just take my total mass, divide it by total of the ions, so I have 2,230.7 divided by 110.5, and I end up with 20.18, I should have 4 sig figs, AMUs, and this would be the average atomic mass of that neon. Oh, you didn't see. Hold on. There we go. Let me run through that again because you couldn't see this. So our average mass is the total mass of the ions divided by the total number of ions. So we take 2230.7 divided by 110.5 and we get 10.18. This is how we calculate average atomic mass from our mass spectrometer. Now, I want you to do one. So let's look at, let's say you were given, we do a mass spectrometer analysis of a sample of boron. And we get this. Okay, so here's my graph. Atomic mass, percent abundance, and we end up with, it spits out something like this. Okay, so for 10, it's 24.8. For 11, it's 100.0. Okay, so this is what it gives us, the mass spectrometer. Now, there are 4 questions I'd like you to answer. I lied, 3 questions. A, how many isotopes are there? B, which is the most stable, and how do you know? And C, calculate the atomic mass. Alright, so I'm going to wait a minute. I want you to do this before we're going to go over it, but I want you to do it. So I'll give you a minute. Okay, well, I'm going to do this now. If you're not done, just pause it for a second and finish and then come back. Alright, so here we go. How many isotopes are there? Well, there are 2 listed, 10 and 11. Which one's the most stable? Now, the most stable one is the one that we have the most of, because the one that we have less of is probably unstable and turning into something else, right, radioactively. So the one that's the most stable is neon 11. Right. The greater the percent abundance, the more stable the isotope. The greater percent abundance, generally the more stable it is. Alright, let's calculate our atomic mass. Alright, so it's 3 steps again. First we need total number. So we add 100.0 plus 24.8. And we get 124.8. That's how many ions are in the sample. We need total mass. So we take 24.8 times 10 plus 100.0 times 11, and we get 1348. And then we divide. And we take 1348 and divide it by 124.8, and we get 10.80 AMU. Probably with sig figs, we have an issue with sig figs here, so this should be 3, so probably my answer should have 3. Remember, you carry out all the math before you do sig figs, so probably my answer should be 10.8 AMUs. Okay. That's where we're going to stop for today. You have some work to do, and we will pick up with more atomic stuff next class. All right, have a good afternoon.